here. Okay, so far, we have covered the first 5 chapters from set and logic to number theory. Now, we're going to learn counting method and pigeonhole principles. Chapter 6. Okay, we're going to start from the basic principles and then permutations and combinations. And after that, we're going to learn the generalized permutations and combinations, then binomial coefficient and combinatorial identities, and at last, the pigeonhole principle will be the end of chapter 8. We must count objects to solve many different types of problems. For instance, counting is used to determine the complexity of algorithms. Furthermore, counting techniques are used extensively when probabilities of events are computed. And also, these counting techniques are used when you make a code. You need the classification of all the cases in a proper way. And these counting techniques will be a useful tool when you do code. First, basic principles. This figure 1, which is a lunch menu of a restaurant, it has 2 types of appetizers and 3 types of main courses and 4 types of beverages. Then, how many menus of your choice? How many possible choice of your menus? How many? You could choose 1 of 2 appetizer, and you could choose 1 out of 3 main menus, and you could choose 1 out of 4 beverages. So all the cases should be 24 cases. You could form 24 different type of menus if you choose 1 from each categories. So, so hamburger, the tea, and so these are, so from here, if you list all those with the first letter of each menus, then it could be listed in this 24 different menus. Here, we did use a principle, which is called a multiplication principle, or it is also called as a product rule. Okay? If an activity can be constructed in T successive steps, and step 1 can be done in N1 ways, step 2 can then be done in N2 ways, etc., and step T can then be done in N1 ways, NT ways, then the number of different possible activities is the product of all those NIs. That's called multiplication principle. Okay? So, the above problem, we have a first step, which is to select the appetizer. We had a choice of 2. For the second step, select the main course out of 3. This N2 is equal to 3. The third step was select the beverage from 4 different types. So N3 should be 4. So total number of the choice of your dinner will be the product of this N1, N2, N3, which is 24. Okay? That was the mathematical proof of the first question. Next, example 1.1. How many dinners are available from case quick lunch consisting of 1 main course and an optional beverage? Which means you don't have to choose the beverage. You can skip the beverage. How many? Then you have 1 choice of main menu out of 3. So N1 is 3. Then how many choices that you have on beverage? There are 4 different types of beverages. and there is one other choice that you do not have the beverage. Then we have 5 choices of beverages, including not choosing. So you have 3, N1 is equal to 3, N2 is equal to 5 choice. So if you do use the multiplication principle, then all the choice should be 3 times N1 times N2, which is 3 times 5, which is 15. So we have a 15 different choice of your lunch, your dinner. Okay. Next example. How many strings of length 4 can be formed using the letters A, B, C, D, E if repetition are not allowed? How many? You have 4, the string of length 4 from 5 letters. First, you have 4 empty spots to be filled. You have, for the first spot, how many choices you can choose? You have from this. So you have 5 choices for the first spot. Then how many choices left for the second spot? 1 letter was used, so you have 4 letters left. So you can choose 1 out of 4. So you have 4 choices for the second block. Then what about third block? The 2 letter was already chosen, so 3 letters were left, so you can choose 1 out of the 3. So you have 3 choices. Then for the last one, you have 2 characters left, 2 letters left. So you can choose 1 out of those 2. So you have 5 choices, 4 choices, and 3 choices, and 2 choices. So the possible number of choices are, by using the multiplication principle, so you could multiply all those choices. Because first, we have 5, 4, 3, 2. So by the multiplication principle, we have the product of those 4 numbers, which is 120. Second, how many strings of A begin with the letter B? How many strings? So this string should start with B. So B is fixed. That's one case. And then how many letters are left for the second spot? There are 4 letters to be chosen. So you have a choice of 4. Then second, on the third box, we have 3 letters left. So we can choose 1 out of 3. And for the last one, we only have 2 letters left. So we have 1 out of 2. So all the cases, by multiplication principle, this is fixed. So 4 times 3 times 2, which is 24 cases for the second part. Third, how many strings of A do not begin with the letter B? How many strings of A do not begin with the letter B? How we can choose it? Here we do use the inclusion, exclusion principle. Total number was what? 120. We already know the total number of the string which starts with B. So what's the total number of string which do not start with B? All we have to do is subtract this case from the whole case. So 120 minus 24 is the number of strings which do not start with the letter B. Okay. So here, we did use the inclusion-exclusion principle, which will be explained later. Next example, in a digital picture, we wish it to encode the amount of light at each point as an 8-bit string. Okay, here, how many values are possible at one point? Okay, digital picture. Okay, we have 8 empty spots, 8 lights. Here, the light can be turned on and off. Second block, it can be lighted on or off. So we have 2 choices on each of these blocks. Okay, on and off. So we have 8 of them. How many different choices of light turn it on and off? How many? That should be 2 to the 8th, which is 256. Okay? Next, use a multiplication principle to show a set from x1 to xn containing an element has 2 to the n subset. How? A subset can be constructed in n successive steps. Pick or do not pick x1. Okay. Next, pick or do not pick x2, etc. up to pick or do not pick xn. So each step can be done in 2 different ways. So the number of possible subset is first one. The possible cases of subset is whether the first element x1 is in or out. Second, x2 is in or out. x3 is in or out, etc. To the last xn is in or out. So all cases has 2 choices independently. So we can use the multiplication principle to find the total number of choices. So we have 2 to the n number of subset, which is same as the cardinality of the whole power set that we have learned in chapter 1, set and logics. Next, example 6. Let X be an n-element set. How many ordered pairs AB satisfies A is a subset of B and B is a subset of X? How? Here, an ordered pair AB satisfying this. Consider this. Then each element in X is in exactly one of A or B minus A or X minus B. Okay. One element in X should be included in only one of these. Then assign each element of X to one of these 3 sets. Then we obtain a unique ordered pair AB that satisfying these. Thus, the number of ordered pair AB satisfying this is equal to the number of ways to assign the element of X to these 3 different sets. So we can make such assignment by following n-step process. Okay. Assign the first element to one of these 3. Assign the second element of X to one of these, etc. And until we assign the nth element of X to one of these. Then how many choices do we have? The first one has 3 choices. The second element has 3 choices. All the way to the last nth element. So each has 3 choices. So by the multiplication principle, so all the possible choices would be 3 to the nth power. Okay. So multiplication principle can be easily adopted when you to count the cases. Next example, so you can read it, you can skip it, you can discuss it in Q&A. Next, internet address. A class A address is a bit string of length 32. The first bit is 0, and the next 7 bits called netted. They identify the network, net ID. The remaining 24 bits called the host ID, identify the computer interface. The net ID must not consist of all ones. The host ID must not consist of all ones or all zeros. Arguing, as in example 6.1.4, we find that there are 2 to the 7th power to 7-bit strings. Since all ones is not allowed as a net ID, so there are 2 to the 7th minus 1 net ID. This, again, arguing as example 6.1.4, we find that there are 2 to the 24th power 24-bit strings. Since the two strings consisting of all zeros or all ones are not allowed as a host ID, there are 2 to the 24th minus 2 host IDs. Then, by the multiplication principle, there are 2 to the 7th power minus 1 times 2 to the 24 minus 2, which is this size, which is 2, what size? So, this is million and trillion, and it's the big number of cases are there. The Class A Internet addresses. Because of the tremendous increase in the size of the Internet, IPv6 version 6 uses the 128-bit address rather than 32-bit address that we introduced here. And this is the example of IP version 4 address, and this is an example of IP version 6 addresses, 128-bit. IP4 addresses have been distributed by INNA to the RIRs in block of approximately 16.8 million addresses each. And these are some explanations that help your understanding on IP addresses. Okay, next. How many 8-bit strings begin either 101 or 111? How many 8-bit strings begin either 101 or 111? So we have an 8-bit string begins with 101. So this is already filled out. So we don't have to worry. So we have only 5 bit, which is empty. How many choices do we have? 0, 1 for each of the blocks. So we have 5 of them. So 2 to the 5th. That's the case that we have, 32 for this part. The one starts with 111. So this first 3 bit was filled out. So we have 5 empty blocks, which has 2 choices each. So 2 to the 5th, which is 32. So 32 and 32. So altogether, we have a 64 8-bit string that begins either 101 or 111. Easy, clear. This is called the addition principle. Suppose that x1, the xt are sets, and that the I set xi has an I element. If x1 to xt is a pairwise disjoint family, then the number of possible elements that can be selected from x1 or x2 or or xt is the addition of those ni's. Okay? So if it's disjoint, then you find the each number of each cases and add all the cases to find the all possible number of cases. Okay, this is an easy example on 10. In how many ways can we select 2 books from different subjects among 5 distinct computer science, 5 distinct computer science books and 3 distinct math books and 2 distinct art books? Okay, how many ways? Okay, how many ways? First, we can select 2 books, one from computer science, one from mathematics. How many choices? We have 5 computer science books and 3 math books, so we have 15 ways over here. And one from computer science, one from art. Then we have 5 choices and 2 choices. One from mathematics and one from art. we have 3 choices and 2 choices from art. By product rule, we have 15, 10, and 6 ways. And these are the sets of elections which are pairwise disjoint. Then we use addition principle to add all those cases, which gives us 31 ways of selecting 2 books from different subjects among the computer science, math, and arts books. That's the way. So sometimes we use multiplication principle and addition principles together to count all the possible cases. Okay. Example 1.11. Yeah, this is a way of choosing chairperson and secretary and treasurer. And we're going to skip this case. And next, inclusion, exclusion principle for 2 sets. Inclusion, exclusion principle generalize the addition principle by giving a formula to compute the number of elements in a union. Figure 1.13, this figure, and then the number, cardinality of X count the number of elements in X minus Y and X intersection Y, and cardinality of Y count the number of elements in X minus Y minus X and X intersection Y. Since the addition of cardinality of X and the cardinality of Y double count the element in the intersection of X and Y, so X, cardinality of X plus cardinality of Y should be the cardinality of X union Y plus cardinality of X intersection Y. This is what you have learned in middle school and elementary school. When you, the addition of this cardinality and this cardinality, count this intersection twice, doubles. So you have to subtract. You have to subtract this in order to find the cardinality of union of those 2 sets. This is a relationship that you know very well. We can write this in this form. The cardinality of X union Y is equal to the cardinality of X plus cardinality of Y minus the part which was double counted, okay, which was counted twice. So this relationship can be written in this way, and we call this rule is the inclusion-exclusion principle for 2 sets. And that can be generalized for the finite number of different sets, not only for 2. So the proofs, there are yeah, you already know the proof intuition, by your intuition, but mathematically, yeah, this can be proved by addition principles easily. Because you are double counted, so you add it, subtract it, and you can easily get this one. And here, the same similar problems, and we're going to cover this one. A committee composed of Alice, Ben, Connie, Dolph, Egbert, and Francisco is to select a chairperson, secretary, and treasurer. How many selections are there in which either Alice or Dolph or both are officers? Think about it. Yeah, as you mentioned here, all we have to do is find the case that Alice can be an officer, and we can count that as a set X, then let Y be the set of selection in which Dolph is an officer. Okay, so find those. He can be chosen to one of these, and she can be chosen to one of these 2. Then we have to consider the both are officers. If you find all those, then this case will be double counted. So we will use the inclusion-exclusion principle to find the proper number. And this idea can be generalized to the finite number of sets for general form of inclusion-exclusion principle. Here, Alice can be assigned an officer in 3 different ways. She can be a chairperson, or secretary, or treasurer. She has 3 choices to be. The highest remaining office can be filled in 5 different ways, because we have 5 different peoples left. Then the last office can be filled with 4 ways. After 2 positions with 2 persons, then only 4 persons left to be chosen. So there are 3 ways to assign Alice. Okay. Then the number of selection in which Alice is an officer is 3 times 5 times 4, which is 60. So cardinality of X is 60. Next, Dolph can be assigned an office in 3 ways. Similarly, we have the cardinality of Y is 60. All we have to think is the intersection of X and Y. Okay, both Alice and Dolph are officers. Then Alice can be assigned in an office in 3 different ways. Then Dolph can be assigned in office in only 2 different ways, because 1 position was filled with Alice, isn't it? So 2 ways left. The last office can be filled in 4 different people who's left, besides those 2, Alice and Dolph. So all the possible cases are 3 times 2 times 4, which is 24. By the inclusion, so cardinality of X intersection Y is 24. So by inclusion-exclusion principle, 60 plus 60 minus 24, which is 96, is the whole number that we were looking for. That's it. That's the example of inclusion-exclusion principle. Yeah, you will see the related problem in exercise from 92 to 97 on the more general cases. I think that's the end of section 6.1, and we will continue 6.2 on Wednesday. Any questions?